Okay, hello everyone. We are just about to start kind of a working meeting trying to figure out some things for our physics project. This is a continuation of something we did a few days ago, trying to understand angular momentum, spin, and maybe charge in the context of these models. This will get fairly technical. Hopefully there will be an opportunity to answer a bunch of questions on the live stream. I should also say this is kind of real science in action, and one feature of real science is it's hard to figure stuff out, and we may go in circles. We may not figure anything out. We may figure something great out. I'm of course hoping for the latter. All right, let's at least just explain. There's a question already on the live stream about what are spin and charge. We'll explain that. That I'm not guaranteeing to explain so much else. Okay, so one feature of particles like electrons is that, well, I should say, there's the notion of linear momentum, which is something that's been sort of around in physics for 300 years, well understood, understood how that works in relativity theory, et cetera, et cetera, et cetera. There's also a notion of angular momentum. Things spinning around, angular momentum is conserved in the same way that linear momentum is conserved in the absence of torques, sort of circular forces. Angular momentum is a little bit funkier in the context of gravitation theory and general relativity. We'll probably talk a bunch about that. But one feature of angular momentum, things spinning around, is that you might think that the size of the angular momentum is proportional to momentum multiplied by kind of the moment, the sort of length arm. You know, you have a thing spinning around there. There's a good thing spinning around. The angular momentum is proportional to the momentum multiplied by the length here. And so one of the things that's strange that was discovered in the 1920s is that even particles like electrons that have always been thought of as being point particles still have an angular momentum, even though they're point particles, even though they don't have that sort of moment arm to make the angular momentum. And what was also discovered is that angular momentum is quantized in units of h bar. The spin of an electron is half h bar, and spin is one of the sort of quintessential quantum mechanical features. It's the thing often used to make qubits for quantum computers. So that's kind of that's what we're going to try to understand in the context of our models. What can spin be? We think we understand what linear momentum is in the context of our models, and it has to do with sort of flux of causal edges, which means essentially the amount of activity that's happening in our hypergraph. So with that, we're going to dive into some more technical things, and I'm going to go off video for now and on to screen sharing here. We're going to start off. So previously we talked a little bit about a possible interpretation for angular momentum in terms of causal edges, but let's talk about what I'm currently, and I'm going to start making actual notes here. And we're going to do this as part of people who are paying attention to the project may have noticed that in the project there is a big section here called live stream archives. There's another big section called working material archives, and there were 337 notebooks in 2020 with all kinds of topics, and this will be another such notebook, and we will call this notebook, I guess, let's go ahead and I will name it here. Hold on one second. And it's going in our physics project 2020, and it is going to get called spin-01. Okay. All right. So what I'd like to talk about is okay. So it seems to me that so in the interpretation of momentum, and we have both Jonathan here and also Jose, who is a general relativity expert. You know, we were talking last time about so linear momentum we think is a flux of causal edges, and we can just for people to see that in our visual summary, the momentum is a flux of these causal edges through time-like hypersurfaces here. Okay, so it will be my hypothesis, which we can now wait for Jonathan and Jose to start shooting down, that angular momentum, that you pick a time-like vector, and that angular momentum is something related to some essentially circulation of causal edges around that time-like vector. So I'd like to understand, and I guess the questions are, so, so this has to do with angular momentum, and is it, question mark, some kind of circulation of causal edges around a time-like vector? And so I guess I have a bunch of questions here. So one question is, in the case of a black hole, but so one thing we know is that black holes have mass and they have angular momentum. And in fact, in general, they have, the no-hair theorem says that they have other attributes that are associated with global features of space-time or global features of the world, like baryon number and so on. So I guess I would ask the question, Jonathan, maybe, in our understanding of black holes and the way that they emerge as causally disconnected, as causal disconnections in the causal graph, do we have an understanding of how we might associate a mass with a black hole, and then what that might give us, what clue that might give us about angular momentum for a black hole?
Sure. I mean, so the mass of the black hole, I think, is relatively easy, right? Because that's just that we know what the energy of it is, because we know the flux of causal edges associated with the singularity through the space-like direction.
Okay, so let's say
work out its mass.
Black hole properties. Okay, so your claim is that when a black hole is formed, so we can find a picture of that, and we can say, for example, let's say we've got a black hole, and someplace here we would have. So I'm trying to understand what your someplace there. Okay, so there we go. So that's an example of a black hole forming causal graph where this.
Well, this is an example of a cosmic event horizon, not a black hole event horizon.
Fair enough. Okay, so how do I get?
So the black hole event horizon, okay, I'm assuming the weak cosmic censorship conjecture here, which I think kind of does trivially hold in our model. But the black hole event horizon would have two differences. One is it would have a singularity associated with it, so there would be a time-like structure that has a disproportionately large number of causal edges in it. And also there would be the event horizon would be slightly different in the sense that you would have causal edges going in one direction only, right? So there wouldn't be.
Let's make a picture of this. Do we have a picture of one of these?
Yeah. Well, I mean, so we have examples of causal graphs where you have some normal form, right, and then that gives you a notion of a singularity. That's a sort of minimal notion of a singularity.
Right. So okay, so I think we need to understand this. Okay, so the claim is, this is not a black hole singularity.
Well, yeah. But, so there are fundamentally two types of singularities two types of event horizons that we support, right? There are cosmological event horizons which are symmetric, like this one, and then there are black hole event horizons which are asymmetric.
I'm not sure I've understood this as clearly as I should have done. So you're saying,
because with the black hole event horizon in our model, all of the causal edges tip so that they point towards the interior. Because in this case, it's not possible for the interior to communicate with the exterior, but it's also not possible for the exterior to communicate with the interior, which is not the black hole case. This is the cosmological case.
Fair enough. I think that's a mistake in some of the things I've written, because you're obviously right about that. Okay, so let's get a reasonable picture of a pure black hole horizon. Okay, so you're saying we can get that. I mean, one trivial way to get that is with a normal form.
Yeah, so we have examples of that for the measurement stuff, right? I think if we drew the causal graph for those models, you'd get something like that behaves at least a bit like a singularity.
Well, let's look at that. Okay, so we've got let's see, we've got one of those probably someplace here. Let's see, we've got something like this, right?
Right.
Oh, that's a big mess, because it's got foliations in it.
Yeah, we just need the multi-way system.
Right, so let's take out that multi-way system there, and that will give us this. And so that has a singularity here because it has a normal form there. And what you're saying is we should generate the causal graph of this, right?
Yeah, and see what happens.
This is going to be a multi-way causal graph.
Right.
Okay, can you understand what that's doing? So there's the piece. Oh, actually, this is nice. This is nice. This is actually doing the right thing. Okay,
yeah.
So hold on. This has causal edges going into that region and not out of that region.
Yeah, exactly. So that's right, precisely. That's how we distinguish the black hole case from the cosmological case. It's a sync point for causal edges.
Well, actually, that's something that is not properly clarified in things I've written. I don't know if it's clarified in things you've written, but okay. So let's try to understand that. So then, in the case of Hawking radiation here, for example, this black hole would continue having internal evolution and would continue having branch pairs interacting with it. So in the multi-way causal graph, it would continue to have edges.
Right. I mean, this is the problem. So this whole normal form idea is only an approximation, right? In reality, this would, as you say, this would have temporal extent. It would just be, effectively causally disconnected from the rest of the universe.
Well, let's get an example of that. How do we get an example of that? So what we want is that the non-multi-way causal graph has, so for example, in this case, we could say something like, I think there's a substitution system causal graph, isn't there?
Yes, I forget how exactly that works.
Let's try this. It's a good sign that it's finding the resource. Okay, there we go. Okay, so that is a very boring yeah, that's a very boring causal graph. But what that is the single the single causal graph. So what we want is a causal graph which has a where if we look at the flow in the causal graph, there's a region you can get into in the ordinary causal graph that you cannot get out of.
Right.
But what we would expect is that as a result of essentially the Hawking radiation type thing, that in the multi-way causal graph, it will be a slightly different story.
Right.
Do you agree with that assessment? So I think what we need to do here is some kind of hunt, effectively. So one of the things we want then is, so your claim is that in this case, the energy of the black hole, the mass of the black hole, is simply the number of sunk causal edges going into this.
Yes, I think so. I mean, so in the multi-way case above, because at least I think I understand how that code works better than the other one. We can trivially give it some temporal extent by just having a rule that takes the 4 x's and adds another x, for instance.
I'm sorry. What were you saying?
If we take those 4 x's, which is the normal form, and we just have a rule that says 4 x's goes to 5 x's, then we can have that as be a temporally extended thing, right? Because it's now evolving independently.
Cool. Okay. So that then, let's evolve that for a few more steps. Okay. So then we've got something.
Partition the universe.
Right. So but we need a layered graph here to be able to see what the heck's going on. Okay, there we go. So there is our black hole. So what happened here, this is a nice example, actually. I mean, what happened there is, we'd probably find a more minimal example than this, but basically what's happening here is this is the rest of the universe, right here. This is the black hole here. And there is flow into the black hole, causal flow into the black hole, but not out.
Right.
But now this is a multi-way causal graph. So where's the Hawking radiation?
So what's going to happen is, because there's disconnection in the multi-way causal graph, one way that it can occur, and it happens to be the case in this particular instance, is that there's also disconnection, or effective disconnection, in the multi-way evolution graph, right? That there are non-reachable states.
Hold on, can you explain this to me? So this is,
like I say, I don't know what this code does. So
well, this is a single slice. So this is a single update ordering, right? So this thing is representing all possible update orders because it's a multi-way causal graph. This
Right.
is a single update order. This is a particular foliation of space-time.
Right. No, I understand, but I remember I looked at substitution system causal graph a few times, and there are a couple of outputs that I didn't understand. So it's
all right. Okay. Well, fine. Let's maybe we can just for fun we can just look at.
Can we see what those events are?
What's that?
Can we see what the events are? That might make it clearer.
Yeah, particularly if we looked at the documentation for this. The BLAF. It's only giving, but what we can do, I think, is let's look.
What happens if we request a vertex list?
We could do that, but I think that's not the one. I think there's one which can actually show. Yeah, what about this? This is useful. Okay, so this would be.
Oh, event labels.
Right. So I think this will actually show the whole thing. So let's take a look at that. So let's get the evolution. We certainly don't need the block random thing there because that was substitution system causal evolution. This, 6. Okay, let's try this. Rather boring, but let's try plotting that and see what it looks like. Okay. All right, so this is presumably the A's, the B's, etc. Let's look at this for a little bit longer. That's pretty hard to interpret. I mean, that claims to be.
It's possible that in this particular event ordering, it's just never, it never gets to the 4x's.
No, it does. No. It gets the 4x's, but it doesn't get to other stuff. So in other words,
it's just evolving the black hole.
That's correct. This is just the black hole. There's nothing. There's no rest of the universe here. It didn't get to the rest of the universe. I mean, we can try modifying this slightly, modifying the initial conditions slightly, see whether we can get it to actually evolve the rest of the universe. Let's put some other A's here. I think then it will not make the black hole, but we can just see what it does. Yeah, hard to interpret. We have to look at this more carefully. But your point up here, this is a reasonable picture, you say, of this, but I'm still asking about branch pairs. And I'm asking about things that quantumly cross the event horizon.
Right. So I think what's going on with branch pairs is, if you imagine, okay, so where there's initially stuff going in to that black hole, right? You can see there's some event on the right where there's an arrow that points in towards that singularity.
Yep.
Okay. So imagine that if at that event there was a branch pair produced. So one of them can be one of the elements of that branch pair can be causally connected to the what becomes that singularity, and the other one can be causally connected to something on the outside world.
I agree.
So now you have a branch pair where they can't reconverge because doing so would violate SR.
I agree. But so that's the case for this. But now, what about things that fall into the black hole here? So in this particular case, this is a one and done black hole where it formed once and then nothing else happens.
Yes, but, of course. Yeah, in the more physical case, there would be more causal edges going in afterwards.
Right. In a better case, there would be additional sort of additional causal edges going into the sink. But each causal edge, I mean, this is something we can model nicely. We need to do this. But each causal edge, as it falls in, can generate a branch pair. Right? So in other words, what's happening then is that the other member of the branch pair is sitting in the multi-way causal graph. The other member of the branch pair will be sitting outside of this region that is disconnected.
Right.
And in fact, that actualizes to some extent our model of the black hole information paradox stuff. Right? We should be able to make a picture that shows explicitly these are the causal edges that wound up inside the event horizon, and these are the causal edges that were sitting on the outside of the event horizon.
Right.
But now, as the black hole evaporates, what will we expect to see? We expect to see one member of the branch pair that sits outside the event horizon, but possibly within the entanglement horizon. Or is that not correct? Is the other, do you see what I'm saying? I mean, so,
yeah.
Okay. Let's understand, how do we see the entanglement horizon in this picture? What's the causal horizon and what's the entanglement horizon? I think to know that, we have to be able to mark what is a branch-like edge in the multi-way causal graph versus what's a space-like edge.
Yes, exactly. And in particular, that's going to tell us, because the problem is it's not clear what the sort of propagation velocity in the multi-way causal graph is, because it's some combination of c and whatever we're calling the entanglement rate. I forget
Zeta. We're calling it zeta.
Right,
okay,
right. And so the ratio of space-like separated events versus branch-like separated events determines the effectively what the natural propagation velocity in the multi-way causal graph is.
Well, but you're saying, I mean, mapping. Look, the multi-way causal graph can be projected both onto space-time and onto branchial space, and those projections have different extents in those spaces.
Yes, right. And so if there are more branch-like separated events than in a different model, it will have a larger effective propagation velocity in the multi-way causal graph.
Yes, I agree. But okay, so one thing we want to do is to find a more realistic black hole here, in which we can mark. So in the case of the string rewrites, the space-like edges are kind of trivial, aren't they? They're not completely trivial.
No, because you need to have some way of computing rule overlaps.
Right, but we should be able to mark, and I don't think we've ever done that, marking in the multi-way causal graph what we can consider to be a space-like edge and what we can consider to be a branch-like edge.
We discussed having an annotated causal graph, but we decided it was too specific. But I agree. I don't think it is. I think it's a useful thing to have.
Okay, so that is a to-do, basically, is to make an annotated causal graph.
Yeah, I will work on it.
Okay, let me make a note here. So, well, annotated multi-way causal graph. Okay, so then what we should see here is, in a more realistic case, we should see certain multi-way edges that are space-like edges that correspond to basically things sort of falling into the black hole. Meanwhile, we should get some things which are branch-like edges. But is it the case that for everything that falls in, there is a branch pair generated?
I think so, because everything that falls in will have an ancestor state, right?
Right. I think that's right.
And so the solution to the information paradox, if you want to go there, is basically that the thing that comes out has to be correlated with the thing that went in, because they're both produced from the same ancestor state.
Right. So everything that goes into the causal, into the black hole region, ends up with a branch pair. Ends up with the other member of its branch pair not going in. Now, could they both go in? Why can't they both go in?
Well, that would correspond to basically branch pairs being produced inside the event horizon, I think.
But so why couldn't it be the case that it's produced outside the event horizon, but both members of the branch pair fall into the event horizon?
Wait, hang on. You're talking about a time extended. You're talking about the branch pair elements as though they're time extended, right?
No, I'm saying that there's a branch There's a branching.
Yeah. And then you're saying one element of both elements of the branch pair eventually fall in. Right? But my point is that a branch pair occurrence is an instantaneous event, right? The branch pair happens, and then the point is one of them is on the event, one of them is inside, and the other one is outside. Of course, the one that's outside might eventually fall back in. There's no rule against Hawking radiation not eventually being, reabsorbed.
Yeah, right. But in the first creation of the branch pair, the whole point is that
either the whole pair is outside, or the whole pair is inside, or there's one on either side.
Right.
And the one on either side is the one we care about.
Right. Both members are internal. Both are outside, or it straddles the black hole. Straddles the event horizon. Okay, well, I think this is a definite, we need a picture of this, and we might try to get that in a few minutes.
We should do a hunt for one of these.
Should we do the,
let's maybe not now, but at some point.
All right, fine, okay. I mean, what is the hunting criterion? The hunting criterion is we need something where there is causal disconnection in the sense that, but you see, I don't think we're going to get causal disconnection because black holes evaporate effectively. We don't have causal disconnection in the multi-way causal graph. We will only have causal disconnection. Well, what is the signature of a black hole?
I think it's a subgraph of the causal graph that has a very high number, a very large number of incoming causal edges. Right? You're basically asking, can we at least in the two-dimensional case, we're asking, or the 1+1 dimensional case, you're asking, can you partition the causal graph into three partitions, such that one of the partitions has a very large number of incoming causal edges from the other two?
Why are there two others?
Because if you're in a 1+1 dimensional space-time, your black hole is somewhere in the middle. It's going to partition.
I see. So you're saying in the strings case,
yes,
you're saying it has to look like this, basically.
Right, unless your black hole happens to exist at the boundary of the universe.
Right. Well, let's see. How would and what are these isolated points here?
Oh, those are probably initialization events. This is forever the bane of our existence,
so to speak. And the fact that they're initialization events that initiate the universe is kind of yeah.
The problem is, okay, in the first version of this code, I had the initialization events actually be causally connected to things. But the problem is, because they're initialization events, they're causally connected to everything. So they make the whole graph a huge mess.
Right.
So I decided to just remove that.
Right. Okay. All right. Let's talk about mass and spin for a minute here. But I really want to come back to this because we really want to make a picture that explicitly shows sort of the solution to the black hole information problem.
Yeah, I
which
think that
seems like we should be able to do.
Yep.
So actually, somebody is asking on our live stream, does the model allow for wormholes? What is the answer to that?
In principle, yes, I think. I mean, I don't see any reason why you can't have Einstein-Rosen solutions for the causal graph if it's sort of sufficiently contorted.
What will it look like? So it will be a causal graph in which, I mean, a wormhole that goes from one part of space to another is quite easy to imagine, although maintaining it is much less clear. And of course, in ordinary general relativity, you have to have negative energy density and other weird things to maintain it.
Right. I mean, what it would basically look like, I think, is you would you'd have something that would look like two independent causal graphs, but just with some structure that connects them, right?
In terms of causality.
With a one-way structure connecting them, yeah.
Yeah, but I mean, look, yes, that's, why is it a one-way structure?
Well, it's one way in the sense that it's, time ordered.
Fair enough. Okay, let's go back to talking about mass and spin, okay? So in this case, the argument would be that the energy of the black hole is associated with the number of incoming causal edges. Right. So now the question is what is interesting about black holes at some level is how parameterless they are. They only have mass and spin and potentially these global conserved quantities like baryon number. So what does that tell us about, is that surprising to us that the only attributes that this black hole can have with respect to the rest of the universe, so to speak, are those? In other words, can we see why that's true from this setup? And then what does it tell us about this possibility about what spin is? So I'm going to make the claim. Again, my meta claim is that spin is associated with pick a time-like vector and then ask the question essentially what the circulation of causal edges around that time-like vector is. Now,
yes, and I agree, and I think I may have a way of actualizing it.
Okay. I think it's tricky because it's not like we can define a curl. We're not in three-dimensional space where we can define a curl. We're in this graph.
But I think basically the construction I was trying to go through on Friday, I think essentially, okay, so in the 1D case, in the 1 plus 1D case, you end up with a time-like hypersurface or something like it, or maybe two time-like hypersurfaces, depending on how you construct it. But in the more general case, what you're doing is you're setting up a time-like cylinder, and you're asking the same question of total flux minus net flux. And that gives you a way, for a time-like oriented cylinder, that gives you a way of evaluating a curl around the interior of the cylinder.
Okay, let me see if I understand that. So my picture is, and again, I want to understand this in terms of the higher dimensional generalizations of angular momentum. So my picture is there is a time-like vector, set up a time-like vector, which in our case will be a bundle of GD6, of time-like GD6, because that's the way we define vectors, basically.
Yeah.
Right? So we have essentially a time-like vector, aka, a GD6. And then we are asking, effectively, you're projecting onto the orthogonal direction to this time-like vector, and you're asking, what does it look like there? So in particular, we could have, if we have, I don't know, if I do a simple, can I do this? What's a vortex in just a vector plot, just so we have a picture to look at? What will make a vortex?
Stephen, I would like to point out that I think this is half of the construction. So orthogonal to a time-like vector, which we could choose to be the momentum vector, there is a three-dimensional space. So you need another vector, a spatial vector, to complete the picture so that orthogonal to this time-like and space-like vectors, you have a plane. And that's a plane of rotation. That's a plane of the angular momentum. So this additional vector, this spatial vector, in representation theory is the Pauli-Lubansky vector.
Yeah, right.
And that's the true spin vector, if you want to call it, orthogonal to the two-dimensional plane.
Okay, so you're saying time-like vector, the time-like vector corresponds, so in the case of, for a particle, we have the time-like vector is like particle momentum vector.
Exactly.
Okay, and then the famous Pauli-Lubansky vector, which is always the, okay, so that is essentially some other vector which defines some helicity. That's some, I need to understand that. So that's a space-like vector. But the basic point you're making, it's, yeah, by the way, somebody's asking on the live stream about, does the initial Big Bang node have an energy which is the sum of subsequent nodes? No, just like there isn't energy conservation in the physical universe. Same issue, I think. In other words, there's local energy conservation in the universe, but there's not global energy conservation because of the expansion of the universe isn't part of the energy equation. Is that a fair, relativist folks, is that a fair characterization, or do you disagree with that? Jonathan.
I agree.
Yeah. So that's actually a point that we should clarify and might be worth a Q&A answer about energy conservation in the whole universe. Can somebody make a note of that so that we should make a Q&A answer about that? It's an obvious question. It's a good question. Okay, can I just, for the sake of my making a picture that I understand, tell me a function that has non-zero vorticity? Is this am I crazy? Is it something like this? I just don't remember what that is not what I wanted. I want something that just has as a vortex here.
Use y minus x.
Very good. Okay, all right. So that's just my picture, maybe incorrect, of somehow what I'm imagining the causal edges look like around this around this direction. But now what you're saying is that, okay, what is the generalization of the whole angular momentum story for arbitrary dimensions? Can we look at some actual formulas? Can somebody put up some actual, can you send me or point me to some actual, I hope I can do better than just look at the Wikipedia page for relativistic angular momentum. But I can do that.
There is a page for the Pauli-Lubansky vector that has the main formula here, I think.
Okay, all right, but so what we're looking at here, and by the way, there's another thing that's going to be a clue for us is the relativistic transformation of the angular momentum vector. Here we go. There's the Pauli-Lubansky pseudo vector.
Right.
Okay.
So that formula in blue in the rectangle. So that shows the angular momentum, the J mu nu. So the angular momentum is always going to be an antisymmetric to tensor, defining this plane of rotation we are interested in.
Mm-hmm.
And then we have P, which is the time-like vector, the momentum, and epsilon with the 4 indices is the total antisymmetric tensor. So it's the tensor that constructs orthogonal things. So by construction, W mu, the Pauli-Lubansky, is orthogonal to both the plane of rotation, the J mu nu, and to P.
Okay, so let's think how we generalize this to an arbitrary number of dimensions, because this creature, the totally antisymmetric tensor, is this a 4-dimensional? Is this only valid in 4 dimensions?
Yes, so the number of dimensions is the number of indices of epsilon.
Right, so what happens, so you're saying the J vector, the J tensor, has to get more indices if we have more dimensions.
No, it's the other way around. It's W that gets more indices. So J will always be an antisymmetric tensor because it's the plane of rotation.
Wait a minute, let me understand that. So you're saying that, I'm still trying to get the intuitive picture of what's going on here. So we've got a momentum vector, which we've defined, and now we're asking, which is, a time-like vector. I'm confused by this because what I'm, okay, explain to me this plane of the
right. So the key idea is that rotation is a plane. So we have the plane of rotation plus a scalar, which you can understand as the multiplicative factor in J, which gives you the intensity of rotation. And so then we have the P mu, the P sigma, which is the time-like vector.
Okay.
And many other spatial dimensions, which are moved into the W. In 4 dimensions, there is only one. Sorry, special indices that are moved into the W.
Okay, so let me understand this. So in the generalization in our hypergraph world, what on earth is rotation? So, I mean, when you say it's a plane, do you mean a set of things orthogonal to a line?
That would be the case in 3 dimensions. In 4 dimensions, it would be the set of things orthogonal to another plane. And in 5 dimensions, orthogonal to a volume, etc.
Is that the right generalization of rotation? Because I mean, to me, the natural thing in our setup would be, you have, let's just understand this. You have a geodesic that defines a vector, right? Now, the first question you can ask is, given that vector, in some graph, that geodesic is a path through the graph. And now what we're asking is, for example, what I was imagining was, let's make a graph here. Okay, so let's make some kind of grid graph. Let's just do a trivial grid graph here. Let's say a 5 by 5 by 5 grid graph. And let's make it a 3D graph. Okay, so what I'm imagining, and it's going to get hard to visualize very quickly, what I'm sort of imagining is, what do we mean? Okay, so to visualize a vector here is easy to, it's just a line through this graph, right? It's just a, I mean, we could probably do that. What are the vertices? Oh, great. Well, okay, so let's just pick two random vertices here, and let's make a, let's do this. Let's say, let's call that G or something, and let's say, we'll say something like find shortest path in that thing between, I don't know, pick a random, actually can we use graph antipode or something to get the opposite one? Well, let's just pick two random things here, 44 and 117. And then let's say we want that, and we want to say highlight graph of GG, and then we want to make a path graph of that. Okay, great. All right, well, that's our geodesic, which didn't happen to be totally straight, okay? But the idea would be, is there a meaningful notion of things orthogonal to that geodesic? And I claim the answer is yes, and I claim it's related to Jonathan's cylinder idea. Because I claim what you do is, from every point on that geodesic, you grow a ball, right? And you can define what it means to be orthogonal to the geodesic with respect to that ball. So actually, Dan on our live stream is asking an interesting question. Is there a natural 2D generalization of a geodesic? I think it's two geodesics. They both start at a single point, and they define essentially a plane. In other words, if we had a different geodesic here, if we had a second geodesic that was, let's say we start from that same 44 node, but we go to a different node, let's say node 70 or something there, I would claim that do you think that's correct, guys? That's the generalization?
Well, I would say that there is a generalization of paths to, so something like cyclic paths can be generalized to spheres, but the notion of geodesic path to a geodesic sphere, that I'm not so sure. So in which sense would it be geodesic?
No, what I'm saying is, given a single point and two geodesics to other random points in the space. So I'm saying you can't, I'm saying there isn't necessarily a two-dimensional generalization of a geodesic from point to point, but it becomes a thing that involves 3 points, an initial point and 2 destination points, as opposed to a geodesic, which just involves 2 points.
Right. It's the surface you'd get by solving the variational problem of defining a surface that, has all 3 points and minimizes area.
Makes sense. Which
is a geodesic surface, I think.
So that's the 2D generalization.
Well, it's a 2D generalization, as Jose says. I don't think it's a unique one.
Right, but we could do the same thing here, where we basically, from every point on these geodesics. Okay, so we could. You're saying we could define a geodesic.
It's a soap bubble problem.
What's that?
It's a soap bubble problem.
Yeah. How does it relate to the strings problem? How does it relate to the string theory problem of minimizing the string action?
It's probably. I mean, yeah, it probably is some it's probably the Nambu-Goto action.
Okay, so the 2D generalization of geodesic question mark is the string, is some kind of string action.
Yeah, I mean, yeah, because you're right that basically the minimization of the Nambu-Goto action is kind of minimization of world sheet area.
Right. Which raises the question. I mean, in this question of how does string theory relate to the things we're talking about, what does it mean? Okay, so to say that if that was correct, then what does that what does that imply about the string theory limit?
Right. Can I go back to what I was saying a moment ago,
Yes.
which actually is relevant to the vorticity plot you produced above?
Okay.
Right. So maybe this will make the idea that I've been trying to articulate a little bit clearer. Right. So if you imagine setting up a time-like surface, right, which would just be in this particular, because this is we're already viewing a time-like projection. We're imagining here, right? We're imagining this is a time-like projection of a 3D causal graph.
Okay, well, by time-like projection, you mean there is the time-like.
We're viewing a space-like hypersurface here.
Is what?
We're viewing a space-like hypersurface.
Okay,
here.
fine. That's what I understood.
Look,
so the
okay.
time-like vector is sticking out of the screen.
Yeah, I mean, let me walk you through my thinking here, right? So in standard general relativity, when you're working in Cartesian coordinates, the way that the simplest way, the way that I think about angular momentum is it's just the thing that you get from the off-diagonal shear terms if you take the space-like part of the stress energy tensor.
Yes.
Right. So the question is, what's our analogy here? And I think it's a very direct one, right? So it's you set up a time-like hypersurface, which in this case would just be a line going through this 2D plot.
Yep.
So you can imagine just a line going from top to bottom. Okay. So now you've got a bunch of causal edges that are intersecting it. But the point is, all the ones that go from left to right are cancelled out by the ones that go from right to left. So although there's flux of causal edges, there's no linear momentum.
I get it.
Because the net flux is zero, right?
So you're saying averaged over your cylinder.
So yeah. So what I'm trying to say is basically, if you now integrate that over all possible angles, so you have all possible time-like hypersurfaces, that gives you a total kind of vorticity around that point.
Wait a minute. You're saying I take a tube, effectively, a time-like tube, and you're saying integrate in the volume of the time-like tube, integrate the net flux from one side to the other. So we could actually do that in this picture, right?
Well, we're not integrating the net flux. We're integrating the total minus net.
I understand, but so let's do that for this picture, because we just project, each one of these arrows can be projected onto, we imagine your time-like surface. So we'll take this thing, y minus x.
Yes.
Okay. So let's go down here and make another picture here. So Jonathan's tube idea. Okay, so we're going to take this, and then what we're going to do is we're going to compute a scalar quantity, which is the projection of each of these things onto the onto your time, your time-like, right? You want a time-like surface here.
Right.
And so each one of these arrows has a projection relative to that time-like surface, if I'm not mistaken.
Yes, exactly. And that's what we want to compute.
Right. And so that will give us a scalar field. This picture will then turn into a scalar field, which then for every one of those possible orientations. So this thing wants to get dotted into a vector, a fixed vector, if I'm not mistaken. So,
yes.
So for example, if I take this and I dot that into the fixed vector, let's say the vector that goes, that's just saying whether it's left or right. So that would be dotted into, if I'm not mistaken, just a 1, 0. Is that right? And then I would take that and I would say density plot of that. Is this correct? Is this not correct? This should be a picture of the flux. Isn't this the flux? Yx, yes, that's the vector dotted into the flux.
Right, so that's the total flux across that surface, across that time-like hypersurface, right? But so what we then want to do is subtract off the net flux.
Okay, and so what's the net flux? You're saying the net flux is integrated over this region.
Okay, hang on, wait. Let me figure out what we're actually doing here. So this is.
So in math terminology, this would be this is like we're integrating for Stokes's law or whatever, or Gauss's law. We're integrating. We have a vector field V there, which is this thing here, and we're dotting it into some infinitesimal surface element.
Right. So the point is, okay, so the net flux in this particular case, what you actually want to do is you would want to sum this density plot for, for each vertical component, if you see what I mean.
So you're saying we integrate it over.
Yeah, right.
Why are we doing that? Is it orthogonal to this, or is it just, why are we only integrating over vertical components?
Because well, it's not orthogonal to that. It's along that surface.
So you're saying we pick the time-like surface,
yeah,
and then we mod down along that time-like surface.
Right. So in this case, you should get 0, right?
Okay, just tell me what computation to do. So you want me to take this thing, and you want me to get, I mean, I could literally take this, I believe, and I could just say integrate over that. I could turn this into integrate, and I get 0.
Right, right. So that's telling you that there's no linear momentum here. Right. So then if you integrate the absolute value of it, it should all of that is then angular momentum. So here we have 54 units of angular momentum, whatever that means, right? So, but that was only relative to that particular time-like hypersurface. But the point is, then what you have to do is, in order to be able to sort of sweep out a full cylinder, you have to integrate that quantity over all time-like hypersurfaces in that cylinder, defined by that cylinder.
All right. Well, so let's write down those hypersurfaces, because what that's going to be is a UV here instead of 1, 0, right?
Right.
So what we really want is that integral as a function of U and V, I think. So we could just say density plot that. Is this going to work? Let's try this. Well, let's just evaluate the integral. We should just be able to evaluate that integral symbolically. He says, how complicated is this? Is this something horrendous? Not promising.
Absolute values are not easy to integrate.
I know. It'll break itself into a gazillion different little pieces.
Yeah.
All right, let's try a simpler case. Let's just try this, just so I understand what that's going to do. Okay, that's easy to understand. So this thing here is.
I think this is a case for n integrate if ever there was one.
How's that going to work? Because it's got parameters.
Oh yeah, true. Well, no, if we want to plot something.
Okay, so let's do a density plot here of that with respect to U and V. Actually, we don't probably want -3. We want -1 to 1. Probably we just want the unit vectors.
Right.
Actually, we really want UV in a circle.
Right.
Okay,
right.
So in fact, let's just do that.
Yeah,
let's just do that. Oh, there it is. Okay, so let's actually do it correctly. Let's do UV element of the unit circle. Is that correct? So that should give us, what is this giving us? This is giving us your total flux.
Yeah, so that's the total flux, which in this case, because there's no net flux anywhere, is purely angular momentum, I claim. So it's telling us the density of angular momentum in our system.
Okay, and what do you think it's going to look like? I mean, that's a vortex core of some kind here that we've got. Right. I don't know what that looks like. Does it have 1/x behavior as you go towards it? What is the vorticity as you go towards the core of that vortex?
It should be 1/r, shouldn't it? Jose, do you know?
Well, it's actually linear. It's actually okay.
Oh,
yeah. That claims to be this measure of angular momentum, so to speak. So what that's saying is, all right, let me try to understand what you're saying here. So the claim is, let's go back again. All right, so we've got, is Jose still with us? Or did Jose somehow?
Yes, I'm here.
Okay, so your claim is we take a region of space-time, we define a time-like vector, we are looking at Okay, I'm still
well,
not quite understanding.
we want instantaneous angular momentum, right? So we have to define, okay, so we take the whole space-time, we define a time-like vector, and then we take a space-like hypersurface, right?
Yes.
Because we want to compute the off-diagonal shear terms for that space-like hypersurface of the spatial metric tensor. So then what we do is we set up, you imagine setting up a time-like hypersurface through that, intersecting that space-like hypersurface.
Right. So we've got three things here. We've got the original time-like vector, and that time-like vector is the time-like hypersurface is kind of pivoting around that time-like vector.
Yes, exactly.
But it in turn is orthogonal.
Sorry,
so
yeah,
again,
Jose, go on.
I can't understand this unless I draw it. Can we draw this, please? So let's see. How do we draw two planes? Do we have an infinite plane primitive?
Yes. But Jonathan, the question is, when you talk about an orthogonal spatial surface, do you mean a three-dimensional or two-dimensional? Because my main point here is all the time that you need a two-dimensional surface. So you always need to find this W vector.
Right. I mean, so obviously, if your space-like hypersurface is three-dimensional, then your time-like, in that case, it's a time-like surface, which will be two-dimensional, that you're summing over.
But it's still the case that whatever it is anchored to this time-like vector, and it is kind of the thing. It is the okay. We've got a space-like hypersurface, which is in d dimensions would be d spatial dimensions is a d-dimensional surface, correct? Orthogonal to the one-time direction.
Right.
Yes.
Now we've got the your time-like surface is again, I think, your time-like hypersurface is again a d-dimensional surface, is it not?
No, I think it's a d-1 dimensional surface. Like in the case above, right? We have a two-dimensional space-like hypersurface.
Yeah, all right, okay.
And we have a one-dimensional
right.
time-like.
So fine, we've got the elements here are the time-like momentum vector. We've got the space-like simultaneity surface, basically. The space-like surface defining, defining our time slice. And then we've got an additional vector, which is an additional thing, which is our time-like hypersurface, right?
Right.
Which the time-like momentum vector goes through. Okay, so this is in d-dimensional, so we'll say in d+1 dimensional, so let's assume we're dealing with d+1 dimensional space-time. And then in that case, the space-like surface is d-dimensional, right? And the time-like hypersurface is, you claim, d-1 dimensional.
Yes.
Because we essentially lost one of the dimensions for the time-like momentum vector, which defines that, which has to be fixed in that hypersurface.
Right.
I would say this third one is two-dimensional.
We're not understanding that. I mean, so because you're looking at the analogy with this J mu nu thing here.
Right.
I'm going to ask another question in a moment, which is about rotating spacetimes and what the metric tensor looks like for a rotating spacetime and how that relates to this. Because one of the ways that we've understood what linear momentum is by understanding boosts, right? Because we understand that if we identify energy as time-like causal edges, as causal edges crossing space-like hypersurfaces, we do a boost, and then we end up with momentum being so. What is the analogous thing? What's the analog of a boost for a rotating coordinate system? I mean, rotating coordinate systems are typically a mess. What is it? The Taub-Nut space or something? What is that thing called? What's the rotating coordinate system space?
I'm not sure I understand. So the Lorentz transformations will be separated in boosts and rotations.
I understand that, but if you want to have normally in our reference frames, we are used to inertial frames that have, I mean, in other words, when you have an inertial frame, you boost something in an inertial frame, it changes the linear momentum. Right? If you were to put something in a rotating frame, you would immediately change the angular momentum.
Right.
But there is no equivalence for rotating frames. Unlike for inertial frames, where there's relativistic equivalence, there is no similar equivalence for rotating frames, right?
What do you mean by equivalence? You can always have you can apply an arbitrary rotation to any frame in the same way that you can apply an arbitrary boost to any frame.
Yeah, but you can't. What is the thing? I mean, okay. So you're claiming, but you can't have a rotation as a function of time. Okay. What is the analog of a velocity? I mean, there's an angular velocity, right? Can you have a frame that has an angular velocity? Because then you would be able to get, that would be an understanding. If we then have our configuration at rest, then the result of a boost, the result of that transformation, giving an angular velocity, would necessarily correspond to something related to angular momentum. But I don't think there's a natural way of defining a frame that corresponds to having angular velocity. Just like in the causal graph, it's natural to define a frame with a linear velocity because that's just tipping the frame with respect to space and time.
Well, if I understand correctly, this would be like just jumping on the frame which is rotating with your object, in the same way that a boost is jumping on the frame that is moving with your object.
Okay, but look, I have a causal graph, and I want to look at a frame that has an angular velocity. What does that look like in the causal graph? Because to have a linear velocity is very easy interpretation in the causal graph.
Right. So I think we always come back to the same question. How do we find this W vector around which we are rotating?
Okay, I'm again confused. So somebody is mentioning killing vectors in the chat here, which seems not completely irrelevant to this story, because that's the I mean, that is the thing that's going to give us the I mean, I think that's related, I would think, to what we.
Yeah, so these are the vector fields that implement the symmetries, the rotation symmetries, for example, the generators of the rotation group.
Right, but I'm still.
But surely all causal edges define a killing vector field by definition.
Because they represent.
Because they, well, the definition. My understanding of a killing vector field is that it preserves the metric, but the causal graph defines the metric.
All right, let's go back to this thing about these planes, because I'm still confused here. Okay, we still have, we're trying to understand. So look, here's my speculation, right? That I have multiple speculations. So first of all, that we're going to find out, I mean, right now, our model graph here does not have any kind of circulation in it, right? So this is going to not have, any intrinsic, any angular momentum or anything interesting like that. But my claim would be that what will lead to that angular momentum is some kind of cycle in this graph. Speculation. Okay? And further speculation that somehow the presence of that cycle in the graph is what in the continuum limit corresponds to pi1 homotopy. In other words, the presence of some vorticity type thing. So the question is, what is the limit? As you look at cycles in a graph, and you look at that graph becoming finer and finer, how does that limit to something that is, I think this is sort of a pi1-ish story, so to speak, here. And further thing would be, the further interesting feature of that is that you could have a big fluffy thing which has many, many, many causal edges, but all you actually care about is this pi1 thing about it. And that feels a lot like what's happening in the case of an electron, for example, where you have this this spin, the electron might be a big thing, but all that matters is something like that homotopy feature, and that would be the reason that you end up with these quantized spins. Okay, that's the speculation. Did that at least make? Okay, and then I have an additional point, which is trying to understand that with respect to the multi-way causal graph, because remember, one of the things we have to be able to explain is this phenomenon in quantum mechanics where, a spin, this sort of a version of the Bell's inequality story, which is a spin that is measured as up. If you then turn your measuring device by angle theta, then you should be able to measure, the probability to get the spin be still up is, cosine squared theta, right? And it's been hard to explain why that doesn't, in hidden variables theories, that tends to go down linearly, not like cosine squared theta. So I think we have a fighting chance of being able to understand if we can have an interpretation of this in, that particular thing when we look at it. Okay, speculation is that somehow comes out because of the some feature of the multi-way causal graph that is different from just saying we're stuck in a single causal graph. Is everybody totally confused here?
No, I agree. I mean, that's.
But okay,
I agree that quantization is going to enter at the level of branchial separation rather than space-like separation. By the way, Jose, I agree. You're correct that you basically need to. I think you do need to define a two-dimensional spatial surface, and then along that spatial surface, you then have to do this integral over individual lines.
Okay, so let's try to nail that down. So what you're saying is,
So in this particular case, you don't have to, because the spatial surface, there is only one spatial surface,
All right, let's make the
with that
3D
time.
version of this at least then. What is the 3D version of this? This is going to be, this is slightly messy, right? It's going to be, if I just have this and 0 there, that will be just a cylindrical thing. Oops. Is this going to be horrific? No, okay, so there it is. So there's the vortex. There's a vortex with a single line going through it, right?
Right. So okay. So in light of Jose's correction, I let me amend what I was saying. So then what you do is you define a two-dimensional plane that cuts through that space, and then you just do exactly the construction I described above with these integrating over these lines.
Okay, but we got two things going on. We've got a vector here that is going downwards in this picture, right? A vector in the whatever direction that is, z direction or whatever it is, right? And now you're saying, in addition, there's a plane that is.
Wait, why do we have a vector going in the z direction?
Because we have a time-like vector.
But this is a space-like hypersurface.
Oh,
if you're saying this is space-time, then this is the same as the
hypersurface.
Yeah, if this is a space-time, then we're just back to the situation we had above. Because then we take a space-like hypersurface and we've got the same picture above. If you fix a value of z,
you're saying step one, project onto a space-like hypersurface.
Yeah, what Jose has basically pointed out, I missed a step, or there was a subtlety I didn't realize, which was that even once you've got the space, if you got the space like hypersurface, you still have to define a plane of rotation. So you have to define a two-dimensional plane, and then integrate over these lines.
Okay, so walk me through this. So we projected onto a space-like hypersurface.
Jose, what was that?
So I would suggest that you always write 3D or 2D, because I think the confusion here is when we talk about space-like surfaces, whether we mean the 2D or the 3D.
Yes, yeah, I agree.
So wait a minute. This is in 3 + 1 dimensional space-time. This would be a space-like hypersurface.
Right.
Right? So now walk me through how we compute. So you're saying we define a 2D plane. And if we had I'd like to be able to draw a 4-dimensional version of this just for our understanding. And I think I can do that because I can make a torus graph.
Right. But Jose's point is that in arbitrary numbers of spatial dimensions, to define a rotation, you still need a two-dimensional. You ultimately still need a two-dimensional plane, right? That construction doesn't vary.
I think I understand, but I need to understand that better. Okay, so is this going to give us, is this torus graph? Gosh, let's make a version of this that we have even a hope of understanding. Okay, there is a torus graph, right? Now, if we have a directed torus graph, are we getting something like this? Are we going to get something like this? I claim we are. I mean, I claim if we have a directed torus graph, we can make something with a similar kind of core like this. Do we have a generalized grid graph? I think we do. Let's look for.
Yeah, it's in the function repository.
Why isn't this auto-completing? Some kind of bug associated with the fact that these are newly added things that don't have, and this is crazy. Look at that raft running away from me. Okay, there's the generalized grid graph. And what we want to do here, okay, so this is circular directed, okay? So what we want to do then is to say generalized grid graph, and then we want to say 10 arrow. Just see how this works. So this is going to make 10 arrow. I don't know why on earth it did that. That's another buggette that should get reported. I don't know why it pasted smart quotes. Okay, so this is then that. So, okay, so let's make our corresponding torus here. Okay, so there's our torus. Whoops, I wanted 3D version of that, so I have a hope here. Do I need the 3D version, or can I look at the 2D version first? So, look, there's our torus. Let's take the 2D version for a second. Whoops. Okay. Is this making any sense? Is this what we were otherwise looking at, or is this not at all what we were otherwise looking at? I think we need to thicken this in this direction. So, for example, let's do this. It's not convincing to me that this is the same thing. What I'm looking for is something where we can ask the question, where we have cycles on the graph. Well, okay, all right, so let's go back to this here. Project onto a space like hypersurface. Then you say we need to define a 2D, plane. I haven't completely understood that. You're saying that's what we need to define the rotation. Is that the point?
Yep. Yeah.
Okay, so if I remember correctly,
things rotate relative to planes.
Okay, so if I look at rotation matrix, then this should have that same characteristic, right? That the rotation matrix, is this right? That's a 3D rotation, okay, that rotates the vector u to the direction of the vector v in any dimension. I see. So the way to think about a rotation in any number of dimensions is that, correct?
Exactly. Vector
that rotates a vector u onto a vector v. So essentially what we're doing then is, so what is the relationship between these vectors and the original vector that defined the space-like hypersurface, the original momentum vector? You're saying these are two additional vectors having nothing to do with the momentum vector. Is that right?
Right. In the Pauli-Lubansky construction, we had in this language 4 vectors, P, W, and then U and V. And they are all orthogonal to each other.
Okay. But so in our case then, in the space-like hypersurface, we've got two additional vectors. So we're defining, and so in our world, those vectors are GD6. So what we're saying is those are two GD6 coming out of a single point, going to two other random points in the space. Is that right? And the notion of a rotation is, so what we're saying, and this might relate to Jonathan's thing, we start, rotation is defined in the graph by starting at a node, pick one geodesic to some other node, then look at other geodesics, and a rotation is defined by taking any pair of those geodesics and asking to, but I don't quite understand how you map the rest of the space, in other words, the rest of the graph in that way.
Perhaps the way to look at this is not comparing to boosts, but comparing to acceleration. So in a sense, if you have a frame that is accelerating, this plane you use to define the frame through the graph is changing. So something similar may be happening for a frame that is rotating. There is some orientation that is changing.
Yeah. But I mean, the thing that I'm already confused by here is we've got to generalize this notion of rotation. And again, I want to come back for a second to the black hole situation that we had at the beginning.
Before you do, can I just ask, what are any of these torus graphs or these generalized grid graphs supposed to be representing?
They were my attempt to make a graph analog of a thing with rotation.
Okay, so they weren't meant to be spatial graphs. They were meant to be space-like surfaces in causal graphs.
Yes.
Okay, yeah, fine. It was just...
I mean, I don't think they've necessarily succeeded at that, but that was what I was trying to do.
Okay.
But I want to come back, let's come back again for a second to Jonathan's idea about the integration of these things. So you're saying, so revising your idea for the statement that we've got, I mean, the obvious integral to do is we've got these two GD6. We can easily pick any, okay, here's an obvious thing to do. A geodesic ball we get by looking at the locus of points that are reached by a single geodesic going out from one point, right? So in other words, if we have a random graph, then the geodesic ball corresponds to center at a point, and then look at all geodesics of length r from that point, right? Yes? Jonathan?
Okay.
I mean, are you with me?
Well, I understand the words. I need to understand the construction.
Okay,
but
so continue. I'm saying we take a graph. Okay, let's pick a graph. Well, okay, we could just take our grid graph for a moment here. We take our grid graph and we ask for, hold on, we just get the grid graph here. And we're saying, yeah, this is a sensible idea that I'm trying to push here. Okay, so what we're going to do then is we're going to say, we're going to say graph neighborhood in this, or neighborhood graph of this thing. So we're going to say, highlight the graph, neighborhood graph in GG, starting with the point, I don't know, 40 or something, and going, is this going to be right? Okay, so this was a little bit, okay, so that attempts to be, I mean, we can make a bigger grid graph here. That attempts to be the points that were graph distance, up to 2 away from vertex 40, right? Yes? Yeah. Okay, so we can think of that as, integrate over all geodesics of length r that go through a particular point, right?
Or integrate over a hypersphere, radius r around a certain point.
Yeah, but operationally in the graph, that's take all the paths of length r that go through a particular point and simply look at, what volume do we get by integrating over all of those? Okay, so I'm going to claim the next thing to do is take pairs of GD6 through a point and integrate over both of those, integrate over them. And then if we do that, but then what we're doing is those pairs of GD6, somehow we're rather than integrating over them independently, this is somehow defining our integration over that plane that you're talking about.
Sure. Okay,
so what exactly is that integral that we want to do there? So we're doing an integral, and with respect to, in the continuous space, that will be an integral just of, R1 and R2 or something that are two vectors. In a continuous space, it's just, that would just be an integral dr1, dr2, right? Where those two R1 and R2 are two vectors.
Right, but that would be integrating over all planes.
But I think that's what you want to do. You just want to have a weighting that is defining your measure of angular momentum.
Okay, you're fine, but you're now talking about something different to what I was proposing.
So you're saying pick a particular pair of GD6, which define a plane.
Right. And then you can measure the angular momentum relative to that plane.
So this would be like a line integral or a rotational of something on the area, differential of area of that surface, which are the same thing via Stokes theorem.
Well, wait a second. The thing, okay. The real thing we want, we need a toy version of this, because otherwise we're not going to be able to figure out what's going on. I mean, if I take this graph, right, and I were to put some essentially circulation on this graph, which I could do by essentially having this graph be a torus graph, if I'm not mistaken.
Right.
Do you agree? So
yeah.
then
I think I have some toy examples of this, but
what's that?
I think I have some toy examples of this.
Okay, can you share them, show them, whatever?
Yeah, of course.
Do you want to share the screen?
If that's okay, yeah.
Yeah, go for it.
Sure. So, okay, so here's an example of a causal graph that contains an example of this form of helicity, right? So you've got, hold on.
Actually, I messed up which screen I'm on here. Hold on 1 second to prevent me from being completely confused here. Go ahead. Yes.
Right. Okay. Right. So okay, this is the causal graph just laid out flat, but then in 3D it's a little bit more obvious what's going on, right? So here you have, if we track this highlighted region, this is a thing that's designed to have some circulation. It's not laid out in the best possible way, but that's
Did you
basically
just make this as we were talking, or was this a pre-made thing?
I was working on this as we were talking. So this is a sort of corkscrew.
Okay, that's why. Okay, all right. Let me. Very cool. Okay, so let me try to understand this.
That's why it's not very good.
Okay.
But so my point is that, okay, if we now lay this out flat, so it's a little bit clearer what's going on, right? So if we, what we can ask is, if we set up these sort of time-like, if we set up like a time-like cylinder here, right? We can ask the number of causal edges going, at least for this particular structure, we can ask the number of causal edges going right to left versus the number of causal edges going left to right. And that, so the net case gives us the linear momentum, and the total minus net case gives us the angular momentum for this particular case. Now, for a higher dimensional thing, it's a little bit complicated, because you basically have to define a pair of GD6 to define a rotation plane, and then measure relative to that.
I finally understood your total thing. I mean, your total thing is sort of nonsense outside of the, well, wait a minute.
It's a way of getting, look. So you have the total stress energy tensor.
Oops, we
right?
lost.
Yeah, those are the only examples I had to show.
I want to say that those examples are interesting.
Fine. Okay,
I mean,
so
you can either continue sharing them, or you can send me that notebook if you want, and I'll put them on my screen.
Okay, yeah, sure. Well, I'll do both in a minute. So the total stress tensor, right? You have these TI0 terms that are your linear momentum, and then you care about the off-diagonal shear terms for the spatial piece for the angular momentum.
Right.
All I'm trying to work out, all I was, my motivation behind this was figuring out how do we subtract off the linear piece so we only get the off diagonal pieces. And the way I think you do that is you do the total minus net.
Well, that's interesting. Okay, so let's just see whether it has the right number of degrees of freedom. If we really believe that, angular momentum is total causal edges. So wait a minute, what are you saying? Total anywhere?
Total minus net.
No, I understand that. For
right.
the minus net, we need to just deal with the fact that we might have a center of mass moving.
Yes, right.
So, but what you're saying is so we subtract off the center of mass degrees of freedom, but now the total, after we've got projected into a space-like hypersurface, right?
Not necessarily. So this is the thing. So we can. What we've been discussing so far is the case where you are projecting, but I think it's actually what I'm trying to say is a bit more general than that. It's that you can have this kind of case where you have sort of helicity of some component, which is time extended, right? So just projecting this into a space-like hypersurface isn't good enough. You actually you kind of need to follow this object in time. You need to know the whole region of space-time.
Why? Because wait a minute. Why? I mean, because that's different from what we're saying. If you want the instantaneous angular momentum, right?
Mm-hmm.
That's instantaneous means a single space, like a single foliation, basically a single.
Yes, right. But something like this, if this corresponds to some object, or to a component of some object, right? This could have no instantaneous angular momentum, but it still has angular momentum if you time extend it a little bit, right? My point is you have to.
I see.
In the same way that you can't just like measure straight graph distances, you have to kind of soften it a bit by constructing these geodesic bundles. I think the same thing is happening here, right? You can't just consider instantaneous angular momentum. You have to soften it by considering a small time extended version.
Yeah, you can't have an infinitely thin space-like hypersurface. You have to have a thickened space-like hypersurface.
Exactly.
Right. So okay, so we're integrating over that thickened space-like hypersurface effectively, and what we've got is you're saying let's measure something we haven't considered before, which is not a flux of causal edges. We've considered the divergence of causal edges, but we haven't considered the total number of causal edges.
Yes.
A rather weird construct. I've been resisting this because I think it's a weird construct. But
well, angular momentum is a weird construct.
Well, maybe it is. Yeah. Well, so let's think about that. So let's say it's total number of causal edges, then minus the degrees of freedom, which are the d-dimensional degrees of freedom in d-dimensional space, the d-dimensional degrees of freedom of the linear momentum, right? So we're saying you are defining total causal edges minus that number of degrees of freedom. I'm just trying to count number of degrees of freedom of this thing.
Mm-hmm. Yep.
And you're saying that by talking about total edges, how does that relate to this whole business that Jose has been talking about defining in the Pauli-Lubansky vector, for example, defining the thing with that single J mu nu rotation piece?
Well, the J mu nu rotation piece is defining this spatial plane, isn't it, Jose?
Yes, so I would say that your construction is global, and I was trying to find a local construction, something that is more like a rotational.
Right.
Because angular momentum can be defined, must be definable locally, because otherwise you may have your tube with the upper half rotating one direction, the other half rotating the other direction, and you would conclude that there is no rotation.
Mm-hmm. Right. So the question is, how local is local, right? Because is it local to the extent of actually a single kind of infinitesimally thin space-like hypersurface?
No way. It's going to be thickened in some way. Just like if we want to figure out momentum density or Lagrangian density, you're not going to do that at the level of individual hyper edges and things. That has to be a thickened continuum limit.
Well, Jose, did I misunderstand what you were saying? Sorry.
No, I mean, perhaps the fact that you have a cycle in the edges already gives you some sort of local notion of rotation. I mean, before you mentioned divergence. So if you can define divergence, probably you can also define rotational, right?
Right.
I think divergence is a lot easier because that's the point that we've, let's imagine we've got this graph and divergence from a region of the graph is pretty easy to define. You make a geodesic ball and you simply ask, what kind of a hedgehog is the geodesic ball? Does it have, edges pointing into or out of the geodesic ball? That's the definition of divergence. So the question here is, can we define something which is more, curl-like? What is the way to define something more curl-like that in what I would hope is the case is that definition can be done both at a fairly small scale on the graph and at a large scale in the continuum limit. And my claim is it's going to somehow relate to some sort of homotopy type story.
Right. So imagine, for example, that you find a cycle in the graph.
Yes.
And if it happens that all neighbors happen to be rotating in similar cycles, then you find.
No, I agree. I think it's to do with the cycle structure. I agree with you.
I'm very confused. So, cycle structure of what?
Of the causal graph.
You have there, right?
So cycle structure.
Yes.
So no, the causal graph cannot itself have cycles. That would be a closed time-like curve.
Yeah. So what do you mean by cycle structure?
I mean some projected cycle structure. I mean you're projecting this thing, and that's
right. So you mean cycle structure of a projected space-like hypersurface of the causal graph?
That's what I mean. Yes.
But I think that's what my construction is measuring, isn't it? The construction we walked through on your other screen.
Well, so wait a minute. You're saying that, well, I don't understand that. I mean, you're saying projected. I mean, there seem to be two different things here. One is something, I mean, and there's a sort of a graph theoretic question, which is, see, it's a bit complicated because what Jose is looking for, and I'm also looking for, is an intrinsic property of the graph in terms of cycle structure, for example. What you're talking about is something where you've taken the graph, you've effectively got an embedding, and then you've got some emergent embedding, and then you're going and looking at fluxes relative to that embedding, right?
Well, my argument is simply that our reconstruction of Riemannian geometry from these causal graphs is not on the basis of purely graph theoretic considerations. It requires taking geodesics. It requires some limiting process.
Indeed.
Right. And so if it is the case that what we want to have is a quantity that is compatible with relativistic angular momentum and therefore compatible with the off-diagonal shear terms of our stress energy tensor, it doesn't make sense to me, at least, to then try and compute that using graph theoretic properties. I think we have to do a similar kind of limiting process.
No, and I agree, but I'm looking, I mean, just like the geodesic ball is a graph theoretic property in some sense, but it's one that has a natural limiting process.
Right. Okay, so yeah, I agree.
But zooming out for a second here, because let's just take your total edges thing, okay? The total edges in the graph. Is that, so relate that to T mu nu. So are you saying that total edges in the graph might simply be the sum of all components of T mu nu?
Something like that. Yes, right. Because it's basically, or at least all components. I think you're removing one degree of freedom because you have to, you have to talk about causal edges in a particular direction or intersecting a particular surface or something.
Okay, but so we've taken T mu nu, we've projected it, we've sliced it. So T mu nu is a vector field throughout space-time, right?
Right. So projecting T mu nu in a particular direction corresponds to taking some hypersurface in this causal graph and basically counting the causal edge flux through that hypersurface.
So, but that's a space-like hypersurface. So you're saying
No, it's T mu nu, so it's any hypersurface.
I see. So your claim is
T mu nu is somehow a measure of globally of causal edge flux in all directions, right?
Okay, so one big question is it's got two legs. T mu nu has two indices, right? And how does that show up here? I would claim that must be showing up through this thing of, for example, having always talking about pairs of geodesics or something. What is the relationship? I mean, because in the case of momentum and energy, we have momentum. We just have a single vector direction. The energy momentum full vector. We just have one four direction. But T mu nu has two directions in it, so somehow that has to show up. And
the point is that you have the quantity from the you have the component from the p mu vector, and then you have the component from the x nu hypersurface.
Yes.
That's why you have two indices.
Right, but I mean, so wait a minute. So one is the hypersurface that is being used to define simultaneity.
Yes.
That's the projection surface.
And one is the component of the relativistic form momentum,
which is where your particle is tooling along, or whatever it is.
Right.
Okay. I know we have to wrap this in just a few minutes here.
Yeah. Well, no, actually, you guys can go on without me. I have to go in a few minutes.
Yeah, I also need to. But we're actually making some progress here. So just to summarize, right? So what we think is the case, and what we have not managed to do. So for example, in your picture here, let's just relate this back to black holes for a second, okay?
Uh-huh.
So in your picture, if we go back to our let me share for a second.
Yeah, of course.
Let's see. So we have we had that black hole picture way before here, right? So you're saying that in this flux of causal edges into the black hole, what we're having to say is that only certain features of, and I think actually we're not that far away from this, that only certain features are measurable, so to speak, with respect to the black hole, right? So we're saying, for example, taking a space-like surface here, we're saying certain causal edges wind up in the black hole. That computes the flux of those causal edges through that space-like hypersurface corresponds to the mass of the black hole.
Right.
But now you're saying some other feature of those causal edges is going to correspond to the angular momentum of the black hole.
Exactly.
And the question is, what is that feature that you can still see, and why can you not see additional features? What is it about the setup of having a sink in the causal graph that causes you to not be able to see other features of the black hole? I mean, intuitively, okay, micro question for the relativity question, the no-hair theorem for black holes. How is that? That's a statement about degrees of freedom in Einstein's equations. Is that right?
I'm not sure. I think it's a statement about the freedoms you can have in a black hole solution, which are very few.
Because the black hole solution has to be localized in space-time somehow. I mean, is that and therefore there's certain symmetries that have to be, by that very fact of localization, that implies certain symmetries with it, I think. And you can only have, that just doesn't leave you enough degrees of freedom to have too much stuff defined. But I'm for example, the fact that the baryon number of a black hole is defined is really weird in this picture. And that, again, should give us a clue about those kinds of global quantum numbers.
Right. I mean, my understanding of the no-hair theorem is it's basically like, it's kind of a classification theorem for black hole solutions, right? It's saying basically that if you have any arbitrary black hole and you kind of if you leave it unperturbed for long enough and you make an appropriately judicious choice of reference frame, most of the degrees of freedom go away. And so basically any such black hole can be described by a Kerr-Newman metric. And it's saying that in some limiting case, the Kerr-Newman metric is sufficient to describe all such,
I see. So your point is, while it's still ringing down after it just had a black hole merger, it still has hair.
I don't know whether that's actually true. That's my understanding. When I first saw the proof of it, that was how
I think you're right. I'm remembering this from a very long time ago. I think you're right, because I think it's still emitting gravitational waves that can give more information about it than just that. I think that's a stationary solutions story.
Yeah, that's correct.
Yeah, my recollection of the proof is it basically just says, yeah, so if you leave it, if you don't perturb it, it eventually decays basically to a Kerr-Newman solution. And then if you make the right choice of reference frame, then most of the degrees of freedom go away, and all you're left with are the degrees of freedom of the Kerr-Newman solution. And that,
right. So the analog of no hair for us is to look at the essentially long, far down the causal graph, what things can still survive as features there. And I think that's worth looking at. And I think we need to understand that. And I think that's going to relate. I'm more optimistic. I agree, Jonathan. I think we're getting there. I think that somehow it's 2GAD6, somehow it's total elements in the causal graph. We're going to get there.
I feel like our intuitions are converging.
Yeah, one more session and we might have it. But I think we probably need a more realistic example, and we probably need some better, we need to go on a hunt for black holes here to get some more realistic examples of string-based black holes.
There is also another operational problem if we want to, before we can understand the no-hair theorem, one of the issues we have is we don't really have any non-trivial examples of like hairy quantities, even in the bulk causal graph, right?
What do you mean? You mean things that like quantum numbers and so on?
Yes, right. So it's kind of hard to say why a black hole might lack certain quantities when we don't even know what those quantities correspond to.
No, I don't think it's going to be as bad as that. I think it's going to be the case that we're basically, they're going to be features of this graph where sort of, because of the fact that it's so poorly connected, my claim is going to be that in the continuum limit, it's going to be the case that that other features of the graph will be necessarily invisible. They will disappear in the continuum limit. That would be my claim. And so we don't even need to know what those quantum numbers correspond to. It's just that only certain aggregate features of the graph will survive in the continuum limit when it has only this type of connection.
Right, but then that tells us the quantum numbers must be in the features that we lost. That's a non-trivial discovery in itself.
I know. That's why I want to do this.
Right.
Because I think it's going to give us some clues about quantum numbers. At least these not local gauge invariance ones, but it's all right. We need to wrap here. Tomorrow we will be doing, I think, I really would like to go on with this, but we'll probably go on with this in a couple of days. Tomorrow we will be doing a Q&A about the backstory to this project and why we're doing crazy things like live streaming our discussions about our semi-confused discussions about black holes and spin and all these kinds of things. Look, I thank you. Yes, somebody's suggesting inviting a differential geometer. We should have that somewhat covered actually, but we don't. But we're still sort of developing our. A lot of people have offered their help with respect to this project, and we need to figure out who we can get involved in these live streams. I would like to comment later on this week, we will be doing a live stream about the relationship to distributed computing, where I think we're really making some very, very interesting progress, and we'll have some people who know about that on this live stream. Anyway, for now, let's wrap up here, and thank you, Jonathan and Jose, and thanks to folks on the live stream, and we'll see you another time. Okay.
Bye.
Thanks.